And part of this talk will touch upon those topics too. So thanks all for coming here. Hello, yeah, I'm Irina. Thanks for organizing. Really happy to be here. In the next few minutes, I'm going to try to make 2 points. One, that we're at a stage where sheer performance is not going to drive adoption of AI further. I think we all know that. That's why we're here. And we need to start thinking more about topics like interpretability. So there's other dimensions on top of sheer performance. And the second point I'll make is that we as developers, engineers, are the first ones that are interested in actually pushing the limits of our models until they break and see how we can do that so that later we can improve on them. So, oops. Okay, there we go. If you needed additional motivation, so touching upon that last comment, you've probably all heard about these cases. Tesla and Uber had several accidents in the last few years while they were they sold the cars, but the cars were not, the autopilot was not officially level 5 by any means. Tesla had the problem of not detecting a truck in time, and the car crashed into it, killing the driver. The driver was not ready to intervene at the time, so it resulted in a fatality. A couple of years later, Tesla was still having problems, the autopilot was having problems detecting fire trucks, and so they were kept crashing into them. Fortunately, I think that nobody died in those. And then around the same time, Uber had an accident where the system actually correctly detected a pedestrian that was pushing her bike across a road. But the global system decided that since it was, I think it was a highway, it must have been a false positive. So it was dismissed and the car ran the person over. Even with those kind of cases, you could argue that the statistics are completely in favor of robotic cars, or at least autonomous to an extent, even level 2 or level 3. But it's only because the stats for humans are just so bad, because we're notoriously bad drivers. And that's the only reason why we can accept these. And not only, the problem with these cases is that every time we have an accident like this, it pushes us back in the eyes of the public, it pushes us back in the eyes of policymakers. Even though they're already safer than most humans at the wheel, people will not trust unless we work a bit on several areas. And it's not only in mobility, it's also other fields like healthcare also have very, very strict processes to approve, to certify systems before they go and physicians start using them. So we really need to work on that. And I care about that because that's basically my background. Most of my background was healthcare, and then I gradually shifted, and for the last couple of years I've been working in mobility. And so those strict certification requirements are things that I keep coming up against. I won't try to define what trustworthiness is. It's probably too fuzzy or too complicated of a term. But what I will say is there's at least 4 areas that we can work on to improve that trustworthiness of our machine learning systems. We've already seen them in your talk. And during the track, we're going to find these again and again because they are really important. I'm going to start with the one that potentially doesn't mean opening up that box and looking at how it works. The most basic one, which is performance, sheer performance, the numbers. Who in the room does machine learning, vision, any kind of software really? Oh, hands up. So most of the people, of course. So you know this. At the most basic level, you want to have your baseline method, you decide what metric matters to you, and you compare it with your new models. And of course, you need that to be automated fast because you're going to do it 1,000 times. And you need to have it completely traced because you're going to have to justify how you got there. And, oops, there we go. And you're going to have to do this close to production. Because if you're just playing around in some toy laptop and then have to deploy it on a vehicle, it probably is not going to be the same thing. So this is the basic setup, but I will argue that this is not enough. This is far from being enough. The first problem we're encountering is that our test sets are probably not too realistic. And most of the time, it can be due to lack of time, lack of resources. But a very typical problem is collecting your data. Say you have access to a vehicle for some months. It happens that that it's during the summer, and then you try to deploy in November. And of course, problems happen, and you start detecting phantoms there, where causing a lot more danger than if you were failing to detect a few pedestrians. If your car or any vehicle starts detecting people everywhere and braking every 5 meters, that's a threat. And the main problem is we have so many benchmarks that are based on data sets that are just not realistic enough. And we call these corner cases, but they're not corner cases at all. They're very common. There are tunnels out there. People drive at night. You're going to have situations where there's going to be very bad light conditions, very bad contrast. So you have to cover all of those. And there's a very interesting paper coming from the Austrian Institute of Technology, where they actually dug up between almost 30 data sets and evaluated them against a specific list of things that they had to cover to be a real good test set. Some of those were Kitty and Cityscapes, which if anyone is doing anything in mobility, you will know that they are extremely popular. And they realized that they were just not enough. They are not realistic enough, and they don't cover many of the cases, many of the scenarios that you're going to find in real life. So that's one of the things we need to start doing, and that's taking a long, hard look at what our test set is like to make sure that it reflects real life. And our problems with the data sets lead me to a very important problem, and that's bias in them. Because a very simple way of seeing it is if I show you this is a toy example, but if I show you this evaluation, we might think two things. One, for most classes, we're not doing that bad. Maybe it's okay. For two, we're going to fail constantly. As soon as we deploy this, we're not going to be able to do anything for bus and trucks, and that's going to be a threat. So naturally, you'll think, okay, what's going on here? Maybe I got the labels all messed up. Maybe the people or the algorithm that was annotating just wasn't working well enough, and then the labels between trucks and buses were mixed. Maybe, or maybe you have a very imbalanced data set. That's also a very typical thing, and that's where that bias gets introduced. But of course, it's not just about bus and trucks. People worry about weaponizing AI, but in fact, that problem with bias affects life. ProPublica did a really interesting research on Compass, which is a software used in the US to predict how likely it is for a convicted criminal to commit another crime in the future. So they examined all people in one specific county. They examined what this software had predicted over 2 years, and they saw what actually had happened in the following 2 years as well. And they realized that that software was extremely biased against Black people. And that destroys lives. Recently, we learned that Amazon had to scratch a recruiting tool that was biased against women. Well, that also affects lives. So my point here is, I'm going to make two. One, this field is still very mature. It is not an easy case. Just like you were saying in your previous talk, detecting bias is very hard until it blows up in your face, when you're already deployed and it affects millions of people, and then you realize that there was something up. And the second point I want to make is that when we worry because our metrics might tell us that we're performing not that bad, but if we're consistently failing for a particular subset, we cannot claim even if we have an average precision of 0.9, or we cannot claim that's robust. That's purely not enough. This leads me to interpretability, because as any machine learning system, any neural network is a model of the world, right? It's perception. It's a model of what we're seeing, and we need to know how it actually works for us to trust it, for us to know exactly why it's making the predictions that it's making. And we care about it because debugging neural networks is very hard. The system isn't going to be crashing. It's just going to doing whatever the hell it likes. And you're going to find out that that was a problem much later. you're going to want to explain those predictions to your colleagues, to your stakeholders, to yourself before you're able to trust it. And you also need to be able to understand your system if you want to generalize better and optimize it. So it's in your best interest to look into it and understand why it's working. And this is an area where, thankfully, there's been a lot of activity lately. You probably have seen these images. Well, hands up if you've seen this. Oh, not that many, I'm surprised. Well, this is a really good paper to read, Why Should I Trust You? And it gave way to a really nice tool called LIME. It's mostly used in structured data, and it tells you, for instance, the features that most contributed to a particular prediction. But it can also be applied to images, as you can see in these above. And they were able to say what part of an image, for instance, contributed to a given prediction. And the example they gave in the paper was a classifier between wolves and huskies. And they realized that while their classifier worked wonderfully, the only thing it had learned was to detect snow, because in their data set, all of the wolf images had snow behind them. So they were making the right predictions for all the wrong reasons. And that's why we need such tools. And thankfully, there's been a lot of activity. We now have a lot more techniques, not just occlusion sensitivity. We have GradCam, which is extremely popular. And the good thing is we can now compare them. And they've been integrated in some tools that these two, for instance, have very recently been released. If you lean towards PyTorch, you might want to look into Captum. If you lean towards TensorFlow, then you have TF-Explain. And they're really nice because you can integrate it into your tensor board. And actually, while you're validating, keep an eye on not just your metrics, not just your accuracy, but why exactly you are doing those predictions and what's going on. And the last topic I'm going to touch on is adversarial robustness. We're going to hear a lot more about this during the track, but I think, so there's two problems with adversarial robustness. One, that we're obsessing over it. So I'm just going to flat out and say it. We're obsessing over it when we still haven't covered the basics, like biases in our data sets or proper evaluations. But at the same time, these are our reality. These are weaknesses that can be exploited. You probably all have seen that image of the panda where they called it noise, but it's an artifact, was overlaid over the image and was misclassified as a given. Well, last year, the same thing was done in the domain of healthcare, where there were images of moles, some of them benign, some of them malignant, and the team were able to switch those diagnostics consistently. So imagine the impact that could have towards, towards everything really. If someone can introduce an attack and switch your diagnostics in your medical files, that's fairly worrying. But it's not just in RGB images. Another team transferred this to the physical world and was able to craft labels, and so hide an attack as what looked like low-grade vandalism. So they just added these labels to a physical stop signal, and the classifier was unable to classify it correctly. It thought it was a 40-mile-per-hour signal instead of a stop signal. And it's not just classifiers. In detectors, we can find the same thing. What you're seeing here in the video is a team that were able to produce an adversarial patch. So if you're interested in surveillance systems, this paper is for you, definitely. Mm-hmm. And it's really interesting how, as you can see, they are moving. You'll see them turning around, and the person holding the adversarial poster is consistently not detected by in this case, it was a YOLO detector. And it's not just RGB, it's also LiDAR. So for those interested in mobility, it arrived. What you're seeing in this video is the correct behavior. So to the right, you see the RGB image, what the RGB camera is capturing. To your left, the LiDAR. And as you can see, when the car approaches the benign box, it's correctly detected. You see how there's a bounding box around it. But when I show you the adversarial case, you'll see how the car approaches the 3D adversarial object, but it's not able to detect it. And again, I suggest that you go to this link. They also have other views, so it's not just in front of them. They have other views where they place the object. So there's been a lot, there's been a bit of activity around provably robust systems. I'm not sure if we're going to get there. In fact, that would be a question for me to researchers. What I'm willing to do in the meantime is to start using adversarial examples. At least in vision, you can try to use them to help you. How? Well, at least during training as an augmentation, during testing, and for interpretability. And I'll get to that in a second. So since there's also been a lot of activity in tooling here, one of the things you could do, and one of the techniques that are used to defend against adversarial attacks is, well, incorporate those adversarial examples to your training data. And hopefully that inoculates the model against these attacks, and you'll be free of problems. Of course, that doesn't guarantee that you'll be free of problems with other attacks, and there's a ton of different attacks out there. Another way you can use it is, since you can generate these adversarial examples, well, not for free, but it's fairly easy, you can add them as a test set. So, of course, you're going to be stress testing your model, and you can also try to produce a report for a certification agency, for yourself or for your stakeholders, saying, well, we are robust against this attack, we have this robustness against this other, and we completely fail against this one. And at least you will know where you are, at least you will know where your weaknesses are. And the tricky one is, how can this link to interpretability? And it links because, well, we don't exactly know why adversarial examples happen. There's been a lot of suggestions, but there was a really interesting paper last year that suggests that these are not really bugs. In fact, the paper is called Adversarial Examples Are Features, they're not bugs. And what they suggested was that they showed us what neural networks focus on, how exactly they reason, what features matter to them. So they distinguished robust features versus non-robust. The robust ones would be the ones that humans pick up on. And apparently we tend to focus more on shape, on outline, instead of what a neural network would focus on, which seems to be more towards texture. So if anyone changed the shapes in a frog, you would immediately say, well, this is not a frog. However, if someone changes the texture in your image, like in the case of the panda, where we added noise, or in the case of the malignant or benign mole, then something subtle changes because it's a non-robust feature, and the human still doesn't know that something changed. It would still say, well, this is still a frog, this is still the same thing, but the neural network would say, no, something has fundamentally changed, and this is not the same object anymore. So this particular feature, or this particular explanation might help us use adversarial examples to expose exactly how our models are reasoning. If you want to play around with them, and if you want to incorporate them into your training, into your testing, there's a bunch of tools. The classic one is Clever Hans. I think that must have been the first one from Goodfellow and his colleagues. But there's been a lot more. And it's really interesting how, for all of these tools, they keep incorporating new attacks because they just keep coming up. And it's basically an arms race between attacks and defenses. And I'm going to stop right here. As a recap, we've taken a look at 4 areas that should help us push our models to the limit and break them just so that we can make them better and more trustworthy. And I really want to push the topic of, we need to take a look at our data sets. We need better techniques to detect biases in data, in our models. And for the other 2, well, there's a lot of research, and for which I'm really thankful, but we need to do a lot more. So thank you, everyone, and I'm happy to hear your questions.
Thank you, Irina. So, questions?
Thank you for your talk. It's quite interesting to hear about these adversarial events. For the Uber accident, I have a comment, and maybe you can comment on my comment. As you said, the system, the leader recognized the person on the street. And so the sensors, they said that there's a person on the street. And then this code was overwritten by the code that said that on the highway can be no person. And so the person was hit by the car. But this means that the Uber engineers has done something by they cheated somehow themselves, because they knew in advance that they would have too many. It was just what you mentioned before. Yes, there would be a emergency stop of a car every 5 meters. And this is, I bet on it. I would bet a lot of money what the Uber car experienced before. It stopped every 5 meters because of a phantom. And what they have done was exactly that. They took the risk and they cheated themselves that the whole thing would somehow work and would work with some luck.
Cheat is well, first of all, I am not a Uber representative. I am not in that team, and there's a lot being written about that case, which I think it might still be being not sure tried, but it's still active, it's still open. But two, I wouldn't ever really call it cheating, seriously. And in fact, the engineer themselves, so from someone who's in mobility, the engineer doesn't really make that decision. It's not part of the engineer's work to decide whether you have to favor one thing or the other. And two, it is a compromise. It's true that you need to think about different scenarios and what is most likely. And there's a lot of discussions around what scenarios you want to support, what you are able to support at different degrees. And that's also, I imagine, why Uber allows users to drive around in these where I think they're level 2 or level 3, so they are not autonomous at all. They still tell their drivers, you need to be ready to intervene, because they know, one, they need to collect all that data, but two, they know they're not ready. And three, it is going to be a problem. The same settings that are valid on a highway are not valid, even as a human driver. You don't drive at the same speed, or you don't look at your mirrors the same way if you're in a highway or on a busy city in downtown, right? And that's something that when you're designing these systems, you need to keep an eye on, because otherwise you will be causing accidents.
Yeah, for me, looked the design like that the pressure to bring it onto the street was higher than the consideration of the risk.
I cannot comment on that.